Welcome to Complexity Made Simple. My name is Paul Allen, and today we're going to do a software tutorial, and we're going to look at the software of choice for design of experiments called DOE Pro. Hope you enjoy it.
Okay, welcome to Complexity Made Simple. In this video, what we're going to take a look at is it's a software tutorial where I'm going to be analysing a multi-output DOE, the software of choice, which of course we've used in the other videos, is software called DOE Pro. So up to now, all the examples that we've done have been single output DOEs, but actually this is much more like a real situation. So we're going to take a look at a multi-output DOE and how to hit. There'll be 3 outputs in this particular problem. How to hit 3 outputs all at the same time. So let's just start by drawing a simple input-output diagram so that we understand what's going on. This is essentially, it is a crash test. And so what we are talking about is car design. We are going to do a crash test, and during the crash test we're going to have to pass some particular parameters, some particular rules. So on the input side of this process, we have 4 variables in the design that we can adjust. The 4 variables are the cross support diameter. Cross support diameter, and that can be varied from 2 to 4. We have the vertical support diameter. Vertical support diameter, which can also be varied from 2 to 4. So this is our design space here that we're creating. We have the box diameter, which is also 2 to 4. And finally, we have the beam angle. The beam angle, and that goes from 35 to 60 degrees. Okay, so there are the 3 outputs. Let's change the color here just to make it a little bit clearer. There are the inputs rather, and then there are 3 outputs that we have to be optimizing. We have to hit all 3 of these. We have to make sure that we pass a test for the triaxial acceleration. That's test number 1 we have to pass. We have to pass the rib compression test. And finally, of course, we need to keep the design cost to a particular level. Can't just spend fortunes getting this right. So we have 4 inputs. We have 3 outputs. And of course, what are we trying to do? We are trying to hit a sweet spot. We're trying to hit more than one target at once. And I believe if we multiply these up, these can be moved in, I think, tenths. I'm not sure what that one can be moved in, but I believe that if we multiply the combinations up in this particular case study, this particular example, there are 16 million ways of setting up each one of these, don't forget. So it's 16 million ways of hitting a triaxial acceleration result, 16 million ways of hitting the rib compression result, 16 million ways of hitting the design cost result. And what we are going to do is we're going to try and hit all three at the same time, find a sweet spot, or of course, this is the great thing about a designed experiment, the test will tell us this can't be done inside this design space. There is no sweet spot. So that's part of what we're going to find out. So let's go to the simulator. Let's find out the current performance, find out the targets, and then we'll do a DOE and we'll create some models and we'll see if we can hit all three of these targets. So here we are looking at the simulator. So you can see we've got the 4 parameters at the bottom here. The 4 parameters that we mentioned that are going to be in the DOE. We've got the three outputs that we're interested in. Now the first thing I'm going to do is just say, well, if we set ourselves at those midpoints, if we set ourselves at those points there, what would the result be? So if we just take a look at the current performance, this has generated 100 data points for us. So if you look at each one, we have design cost. Currently the design cost is very cheap. It's just £30. We need to be between 300, we need to be below £300 on the design cost. Let's take a look at the next one. The rib compression. Now the rib compression, well, the design is cheap, but of course it's not working, because where we want this result to be is below 11, and we're currently hitting 15.77, so we're currently failing this test, but it's a very cheap design at this point. So we need to be below 11. And finally, triaxial acceleration. Well, we're currently hitting 19.89, not good enough, failing the test. What we need to be is below 15. So just so we know where we're going, let's just put those on our original diagram so we know what the targets are. So the 3 targets, we got £300 on the design cost. It's not money, is it? Less than 11 on the rib compression, and less than 15 on the triaxial acceleration. So there are our 3 targets. So here, this is our problem that we need to address. So let's go back to the simulator now. What the simulator is just going to do for me is it's going to simulate us doing a designed experiment. All right, so it's going to simulate a series of experiments, and then we're going to use a model to hit the sweet spot if we can. Let's go back to the simulator. Okay, so here we are. We've done the current performance. Now what I need to do is to simulate us doing an experiment. Now because there's 4 factors, the experiment we're going to do is known as a full factorial. So we're going to do a 16 run full factorial design. And this thing is just going to create some data for me, going to create a DOE for me to understand the system that we're trying to optimize. So there's the DOE. I need to put this into Excel. So let me just get the computer to paste this across into Excel for me. And then we'll take a look at the DOE that's been created. So here's the DOE in Excel. We've got Sigma Zone running, so I've got DOE Pro running up here, look. And what I've effectively got, look, is 3 separate pages of results. So we've done the same DOE, and in the same experiment, we've done design cost, rib compression, triaxial acceleration. So now I can analyze these results. So here we go. I'm going to go up to Analyze Design. and I'm going to plot some graphs first. I'm going to plot the marginal means plot. Now, because I'm sitting on the triaxial acceleration page, it will only do the plots for this page. So we'll do the triaxial first. I'll have both the S hat and the Y hat. Then I'll do the rib compression, analyze design, marginal means, both S and Y. Okay, so we've got some graphs for the rib and the triaxial. So let's go take a look at these. Now, what I'm going to do, look, is I'm going to take a look at S, the standard deviation, the spread. So this is all about, it's the S graph. What is this about? This is about the spread. It's about the consistency of the particular result. And what I need to do is control the spread in both the rib compression and the triaxial result. Of course, there will be no spread in the cost calculation because it is a straight calculation. You'll always get the same answer. But in an actual crash test, when I'm doing the crash test, I'm going to get different results for rib. I'm going to get different results for triaxial. So you can see, look, here in this box here, it's telling me, whoops, the box diameter. The box diameter is driving the standard deviation. Now, where do we want to be? Well, we want to minimize standard deviation, which means being at the bottom end of that brown line, which means putting the box diameter to 4. Now, I'm going to write that down because that's important. I'm going to put that back into the system when we design the result. So when we design the optimized conditions, box diameter has to be at 4 to control standard deviation. So let's just see if it controls standard deviation for triaxial, and it does. So this is a common decision. This is what you're looking for. I have a common decision to control 2 outputs, control the spread of the 2 outputs at the same time. So there's my decision. Now then, let's go to Sigma Zone again. Now what we're going to do is analyze design. I'm going to have multiple response regression. Now what we've got are 3 models side by side. We have a model for design cost, a model for rib compression, and a model for triaxial acceleration. I'm going to proceed as I normally do. I'm going to take terms out of this model that shouldn't be there. So I'm going to take those terms out of the cost model. I'm going to remove these terms. So as a reminder for those that are having a reminder on how to regress DOEs, what am I taking away? I'm taking away the p-values that are not red or blue. So the p-value is telling me whether the term should stay in the model. It's telling me whether the term is real or not, or just noise. So you can see there's an awful lot of noise going on in these models that doesn't need to be there. So I'm going to take those terms away. Oops, like that though. Take those terms away. And now I'm going to hit regression again. So analyze design, multiple response regression. And now what we'll get is 3 true models for our problem. So you can see we have a model for design cost, a model for rib compression, a model for triaxial acceleration. The model contains some interactions because some of the variables interact with each other. Most important, if that's the case, that we have an equation that can understand the interaction, because interactions create confusion typically. So now I have the models. What am I going to do next? Well, now I'm going to the multiple response optimizer, and I'm going to tell it the 3 targets that I want it to hit. Now, important here, I've got to tell it that box diameter can't be moved from 4. So I'm going to type 4 in both of those box diameter cells there, which means that the computer now cannot move the box diameter, because that's how we control the spread. That's how we control the consistency. I don't want the computer playing with that. Then I'm going to click through to the window where I can put in the constraints. So the design cost should be less than 300. Add constraint. Drop the menu down. Rib compression less than 11. Add constraint. Triaxial acceleration less than 15. Now just before I add constraint, you'll notice there's a weight in here, and the weight appears at the top. If I click that now, look. So you can see each one of these requests has the same weight. The weight is a means of telling the computer one of those outputs might be more important. And all I have to do is change then the number relative to one another. So for instance, if the triaxial was most important, if I'd have changed the weight to 55, the computer will do that optimization first, and then it'll optimize the other two behind it. So in other words, if there's going to be a compromise, the compromise would be made in the cost and the rib compression. It won't be made in the triaxial acceleration. So when you adjust the weight, you only have to make them slightly different to effectively get the computer to prioritize when it's doing multiple outputs. But now we've put those requests in, I'm going to hit optimize, and you can see because it's come back with 50 out of 50 for every one of those, it's saying that actually I can hit all of those targets, no problem whatsoever. Okay, so that being the case, I'm going to put the settings into the worksheet. So what are the settings? So let's have a look. We've got within the yellow fields, let's blow this up so it's a little bit more obvious. Here we are, look. So in the yellow cells, in the middle there, in the middle of the table, these yellow cells here, it says we're going to put cross support to 2.36. I think that will probably have to be 2.4, rounded up. We're going to put the vertical support diameter to 399. I'm going to put that to 4, rounded up. The box diameter is going to be 4, and the beam angle is going to be at 60. And most important though, before we go off and do this, look at the 3 predictions. It says we're going to hit a cost of £288. We're going to hit rib of 9.33, and we're going to hit triaxial of 14.25. Okay, so they're the actual predictions. Now that's the true test of whether the model works. The true test of whether the model works is not that we're the right side of the tolerance or that we pass a particular test. We want to hit what the mathematics predicts. So now let's go back to the simulator. We will dial those values in and we'll see if we hit the predicted values. So here we are back at the simulator. I'll bring up the CPK diagrams. We'll get rid of all the previous data, and then I'll dial the values in. So I need the first value to be at 2.4. The vertical support diameter was 399 actually, but I can't do 399, so 4 is the closest I can get. Box diameter was 4 and beam angle was 60. So let's now generate 100 samples. This is this is replicating, going back to the machine, going back to the process, and getting 100 more data points out of your process. Okay, so design cost was supposed to be 288. We've hit 289 with £1 out. Rib compression was supposed to be 9.33. We've hit 9.03 on the rib compression. So pretty much where we're expecting to be at the moment. And finally, The triaxial was going to be at 14.25 was the prediction. We've hit 14.22. This is working brilliantly. The maths is working superb. And think about what the problem was here. Let's go back to our PowerPoint presentation a second. And let's think about what the problem was. Well, the problem was that we got 16 million choices times 3. So 48 million combinations, and somewhere in that lot there is a sweet spot to hit all 3 of those targets. And we've done exactly that by using a designed experiment. Now, for those of you that haven't seen DOE before, exactly what was going on? Well, it's very simple. There's a set of tests that should be done. So if we talk about, this was the cross support. So this is variable 1. The tests that were done were at the extremes, at the 2 and the 4. But then there was also the vertical support. And that, of course, was 2 and 4. And those tests, so we've gone 2 and 4 there. We've gone 2 and 4 there. We've tested at these corner points. And we've got a third variable, which was the box diameter. So, of course, now if we put all these combinations in, what am I doing? Well, I'm testing at the corners of this box. Okay, so this, going backwards now, this is the box diameter. And again, where can we go? Well, 2 and 4 on this. Now, obviously, there's a fourth variable, and this would turn it into a 4-dimensional cube, something I can't draw if we add in the beam angle. But basically, because if we add another combination in, what we've really got is 16 corner points. Now, the 16 corner points, that's the best place to test. So if you're trying to do experiments and you want to learn the most out of a system, where's the best place to test? At the corner points of the design space. So we've tested 16 corner points of a design space. That allows us to make brilliant models, and it allows us to hit 3 targets all at the same time. Only design of experiments can do this, because, as I constantly say, DOE is the fastest way. It's the fastest way to get process knowledge. Only a DOE can do this. Your skill would never be able to understand these 48 million combinations so well and so quickly. 16 tests, and we find the sweet spot. Only DOE can do this, because it is the fastest way to find process knowledge.
Well, I hope you found that useful. If you've got any questions about that topic, or indeed anything to do with Six Sigma or Lean for that matter, give me a call, and I hope to hear from you soon.